This is a brief discussion of how temperature is related to heat and how we can actually learn something about heat simply by making some measurements of temperature. Our learning goals include the relationship between heat and temperature and how that leads us to some capabilities for measuring heat change. I want you to consider a really simple experiment. Okay, so let's look at this picture and talk about the different aspects of it. Temperature is being plotted on the horizontal axis. And in particular, we're going to look at a change that occurs between two temperatures, T1 and T2. Now, on the vertical axis, we're graphing heat that's added to the system, and that's going to change from Q1 to Q2. So you can imagine this is an experiment where we're taking some water and we're adding heat in a controlled way, or we're adding temperature in a controlled way, but when we add the heat, we're measuring the change in temperature, or vice versa. All right, what we're going to get from this is an understanding of how the two are related to one another. And what's interesting about this is that we find in all cases when we do this kind of experiment that in fact they're linearly related. That is to say, the plot that we get from graphing data points in such an experiment is a straight line. And that line has a particular slope that I'll call C as we go through this. All right, so now as we're heating this thing up, we're going to higher and higher heat content, and we're changing temperature from T1 to T2. The total temperature change going all the way across is delta T, that's the difference between T2 and T1, and the total heat that's absorbed in this is the difference between the top and the bottom, which we'll call little q is equal to Q2 minus Q1. Now, because this is a linear plot, that means that the heat is related to this slope, C, times the change in temperature. So we can basically write a very simple equation that Q is equal to C times delta T. And this is essentially at the heart of all we're trying to talk about in this particular video. Delta T is the change in temperature. This C that appears here as the proportionality constant is something called the heat capacity, and that's going to be the central focus for us. So let's talk about that heat capacity a little bit. A definition of heat capacity is it's basically the amount of heat that a sample needs in order to raise its temperature by 1 Kelvin, or 1 degree centigrade, since 1 centigrade and 1 Kelvin are the same amount of temperature difference. Now, this heat capacity is an extensive property, which means that if you have more of some stuff, it's going to have a higher heat capacity. Or if you have less of some stuff, you'll have a lower heat capacity. So it's sometimes useful to make it into less of an extensive property by talking about a particular kind of heat capacity called a specific heat capacity. And this refers to the heat capacity of a single gram of that sample. This way, if you need to treat a sample that's bigger than 1 gram, you can always multiply by its mass to get its total heat capacity. But you can talk about a number now that is a unique fixed number for that substance. Now what this means then is that the heat that's transferred is equal to the mass times the specific heat times the change in temperature. Now why might this be useful? Well, we can now tabulate the specific heats of different substances, since the overall heat capacity depends on how much stuff we have, and that could be different from one measurement to another. The specific heat capacity is a much more useful thing to tabulate. So here are some representative specific heats, showing on the left-hand side a few representative nonmetals, on the right-hand side a few representative metals. By and large, you'll notice that the nonmetal substances have very high heat capacities, very high specific heat capacities, with hydrogen having the highest, 14.3, water actually a fairly high heat capacity of 4.184, and so forth. The metals, on the other hand, tend to have lower heat capacities. Sodium is 1.23, aluminum about 0.9, and so forth. Now, you shouldn't necessarily get wrapped up in nonmetals have high heat capacity and metals have low heat capacity, because it's really a measure more of the mass of these different substances. But one thing you can take to the bank, and that is that a higher specific heat means that more heat must be added to raise the temperature. And this has a lot of consequences for us because water has a very high heat capacity in general, which means that it can absorb a lot of heat without raising its temperature very much. This is part of what makes cities that are by the ocean more temperate in their climates, because the water in the ocean is absorbing a lot of heat without raising the temperature. It's also why if you park your car in a parking lot in San Antonio in the summertime and you leave it out most of the day and the sun's beating on it and you go out and you touch your car, it's really hot because the metal of your car has a low heat capacity, so it doesn't take a lot of heat to be absorbed for it to rise in temperature quite a bit. We'll be using these concepts a lot in the coming lessons as we talk about calorimetry and a variety of different ways that we measure heat change in reactions.